So the final talk of this morning session will be Shigeru Ida and having a more sociological view of planets and studying them as a population.
Okay, so I talk about the planet population synthesis. The authors of the chapters, the chapter is Willy Benz and myself, and Jan Albert and Doug Green and Christophe Montassini. I'm Shigeru Ida, so from ELSI. ELSI is the Earth Life Science Institute, new institute at the Tokyo Institute of Technology. Today, I talk about 4 issues. So what is population synthesis, and what we needed, and what we have learned from it, and what's next. Okay, so. Okay, so what is population synthesis? Even if we assume the planetesimals already formed from dust grain, there are so many processes after that, like planetesimal accretion, migration, and gas accretion to the core, and the planet-planet scattering. So these processes are many different physics. So we try to extract the essential physics from each process to make the tractable models based on the first principle expensive computer simulation. Tractable means a semiotical formula or simplified simulation or Monte Carlo. So given the initial disk condition that inferred from the observation, we integrate this tractable model to produce the planetary distribution. Then we can compare the theory with observation. Okay, so, okay. Then why we need population synthesis? Of course, this is the best tool to compare the theory with observation. So such kind of direct comparison with observation is not easy only through the detailed simulation for a specific process. So let me describe my case as an example. Previously, I was working on the n-body simulation of planetesimal scattering and growth and oligarchic growth or something like that. Of course, such n-body simulation is very important. But at the same time, I realized that the simulation is very expensive. So the simulation must be limited to the local one or simulation only in the inner region. If the simulation is local, it's not easy to include long range and migration, orbital migration. Also, why n-body simulation limited to the inner region is simple. In the outer region, physical radius of the bodies, physical radius of the planetesimals are 3 orders of magnitude smaller than the Hill radius. So calculating the collision between the planetesimals is really hard. So it means that it's not easy to simulate the formation of giant planet because formation of giant planet often occurs in outer region. So there's another method, so Eulerian statistical method, which follow the evolution of the mass function of the planets at each orbital radius. Then the outer region is okay, but because it is Eulerian, it's not easy to include the migration and the scattering. Then some paper like Bromley Kenyon try to do a hybrid code of the n-body and the statistical method. But the planet formation include other processes, and for the comparison with the observation, we need many runs, so we need fast calculation to do statistical comparison with observation. So we considered developing the population synthesis. So this scheme, this simulation is a Lagrangian, which means that it follows the evolution of the each embryo, so growth and migration and scattering. So myself and Doug Green pursue faster calculation, so using the semi-analytical formula or Monte Carlo, and other papers by such as Curie and Miguel et al. They are all same line. On the other hand, Montassini et al. Pursue more detailed models, kind of a hybrid model or something like that. Other papers by Thomas et al., Bromine Canyon, they are same line. So these approaches are complementary to each other. So using the population synthesis, we try to explain the existing observation data. But note that the population synthesis cannot produce an arbitrary distribution with the ad hoc choice of the parameters. And change in the parameters result in some trend of the change in the result. So it's not arbitrary. So the comparison with the observation can constrain the theoretical models. Then through these processes, we can clarify what are the key in the planet formation theory and predict the future observation. So this is one example. First, we set up an initial seed of embryos based on the oligarchic growth model. So here, some seeds are set up. Then we calculate the planetesimal accretion and migration, gas accretion to the core, and the scattering, or giant impact, something like that. And then we get the final state. In this case, we have some closely packed rocky planets and gas giants and icy planets. Then we repeat this kind of calculation again and again. So then we superpose a final result. Then we have this kind of final distribution. So with this distribution, we can compare the theory with the observation. There are so many issues to be discussed, but today I focus on the 4 issues. So regarding the comparison with observation, I want to discuss about the link between the diversity of exoplanetary system and the initial disk solid mass. And the second point is that the planet-planet scattering can be responsible for the eccentricity of giant planet. And also, it could be responsible for the distant Jupiters in the circular orbit. Okay, so regarding a theoretical point, I want to discuss about the type 1 and the type 2 migrations. Okay, first, diversity of exoplanetary system. Our model is based on the co-accretion model. So the co-accretion model produces many small mass solid planets. So here's some example. This is mass and the number of the planet, and the number of planets increase with the decrease in the planetary mass. So recent observation also show that there's such a trend. Number of planet, frequency of planet increase with the decrease in the planetary mass. So already Rabbit talked about that formation of gas giant. If these solid planets exceed some kind of threshold mass, from a few Earth mass to 10 Earth mass, then the runaway gas accretion starts. Then the planetary mass jumps up by the factor 10 or 100 or more. Then it affects the whole system. And also the predicted solid planet mass it's proportional to the 3/2 of the solid mass. So this dependence is relatively strong. And also the observations suggest that the disk solid mass have the large diversity, like 10 to the minus 5 to 10 to the minus 3 stellar mass. So this change causes planet mass change, then it makes giant or not. So here are some example. So this is semi-axis and eccentricity. And if we start with a low mass disk, then we just get a small, rocky, and icy planet. But if we increase the solid mass, then the gas giants are formed, and in the massive disk, several gas giants are formed, and they become dynamically unstable and eject, and some very violent process occurs. So in this point of view, already Ravi talked about the metallicity dependence and the stellar mass dependence is easily understood. In a metal-rich disk, of course, solid mass is large. Then we have the gas giant. But note that the frequency of the superls does not increase with the metallicity, or rather decrease. Because in a metal-rich disk, gas giants are often formed, and they are often become dynamically unstable. Then it inhibits the formation and the retention of the superls. And also note that the disk mass has a large dispersion, like two orders of magnitude dispersion. So even if low metallicity case, if we consider the massive disk, then the solid mass itself is large enough to make a gas giant. So Jupiter mass planet can be formed around the low mass planet, low metallicity stars. Also the stellar mass, because the solid mass is proportional to the stellar mass, then it's very hard to make the gas giants around M dwarfs. So it is also easy to understood. Okay, next, planet-planet scattering. So far, N-body simulation of 2 or 3 giant planets have been extensively studied. And they show that the functional form of eccentricity distribution is consistent with observed distribution. So, but these N-body simulations set up the initial condition, arbitrarily. But the population synthesis can provide an initial condition. So we used some Monte Carlo code, and of course, this code, this scheme follow the conservation law imposed by the celestial mechanics, and some chaotic part is calibrated by N-body simulation. So this is Monte Carlo, so it is extremely fast. On the other hand, Aribe et al., the most recent paper, they use a direct N-body simulation. Of course, it is more accurate, although the calculation is more expensive. Again, these are complementary to each other. Okay, so let me show some result of the eccentricity distribution. This is our result, and this is mass of planet, and this is eccentricity. So bottom panel shows that the theoretically predicted all the planet. And in the middle panel, I extract the planet that are currently observable by the radial velocity survey. And this panel shows the observation. But I just take out the planet that have been discovered by radial velocity survey. As you can see that the eccentricities increase with the planet mass. And our theory also reproduces such trend. It is very easy to understand because as I already showed, in massive disk, very big, giant planet formed, and they tend to be dynamically unstable. And then some giants are ejected, and the others are eccentricities are excited. On the other hand, in the medium mass disk, gas giants are formed, but sometimes they are lonely or just two. In that case, they tend to be dynamically stable. So the eccentricity is not excited. Also, the NMOE simulation by Raymond et al. Shows a similar trend. And this is a semi-axis and eccentricity. You find that the eccentricity increase with the semi-axis. Of course, some tidal damping of by the star it can be responsible for the eccentric damping in the closest planet. But we find that if the planet-planet scattering is responsible for the eccentric excitation, then the maximum eccentricity is given by the escape velocity from the surface of the planet scaled by the Kepler velocity. Then it increases with the square root of the semi-axis. Actually, so this line is eccentricity increase proportional to the square root of the semi-axis. Okay, and this scattering could be responsible for the distant Jupiter in a nearly circular orbit. We find that some cores form, and this core is scattered by the Jupiter mass planet, big planet. Then this core get a highly eccentric orbit. But this core spend most of the time near the apocenter rather than pericenter. So this core starts gas accretion. Then this core accretes gas in the distant region. And then this orbit circularized. This kind of process was already found by some hybrid code by Ed Thomas. And we calculate the frequency. So in this particular simulation, frequency of the gas, this is around the solar type stars. Frequency of the giant planet with the more massive than the 10 Jupiter mass and beyond 30 AU and eccentricity smaller than 0.1, we found that 4% of the system have such kind of giant planet. We also find some multiple cases, because this is based on the scattering of the cores by the giant planet. It is possible that the 2 cores are scattered and 3 cores are scattered, and then start gas accretion in a distant region. Okay, so now I move on to the theory things. First, I talk about the type 2 migration. So it is also a very big problem. As already showed that the migration rate of the type 2 is described by the disk accretion rate, disk accretion velocity, when the planet mass is small enough. When the planet mass is large enough, then there's some factor. Then the type 2 migration is slow down. Also note that this migration rate corresponds to the local viscous diffusion timescale, which is much shorter than the global viscous diffusion timescale. So this corresponds to the disk lifetime. Then which means that most Jupiters migrate to become hot Jupiters, because this timescale is much shorter than the disk lifetime. But the situation is not so simple. So Modassini et al. Also use a similar formula. There's some factor difference, but the formulas are very, very similar. But our result and their result are very different. I mean, the distribution of gas giants are very different. So this is because the treatment of the gas flow across the gap is different. So let me explain this. Already discussed about the gap opening. So there's some planetary perturbation and the viscous torque and the thermal condition. This is a pressure gradient. Then when the planet becomes like larger than the 0.1 or Jupiter mass, then the gap are opened. So in our case, we regard the planet open up gap when the viscous condition is satisfied. Then the type 2 migration start, like at 10 Earth mass or 30 Earth mass. But after that, we allow the gas accretion onto the planet because we assume that the gap is not so clear here. But eventually, we stop completely terminate the gas accretion onto the planet when this kind of condition is satisfied. So when the planet mass becomes a few Jupiter mass or 10 Jupiter mass, we completely stop the disk accretion. So in our case, type 2 is relatively efficient. On the other hand, Modassini et al. Allow the gas accretion after the gap opening, always 3 pi sigma nu. So it is equal to the disk accretion rate. So in that case, a planet becomes big and big, then the type 2 migration tends to be planet-dominated, slow down phase. Also, they assume the efficient photoevaporation. So it remove the disk mass. Then the type 2 is more and more planet-dominated. As a result, so here is the semi-axis and the mass. In our case, migration is so efficient. Type 2 is so efficient. So we produce, many hot Jupiters. So this is an observation. Here, I take out the planet discovered by radial velocity survey. I didn't put the planet discovered by transit survey because the transit survey is highly biased to the closing planet. So you see there is some pileup of the hot Jupiters, but not so strong. And the pileup is found beyond 1 AU. So in our case, hot Jupiters are produced too many. And we don't find any clear pileup beyond 1 AU because the type 2 is so efficient. On the other hand, this is Alve et al.'s result. In this case, type 2 is not so efficient. So the hot Jupiters are very few, not so many. So even if we use the almost same formula, final distribution of giant planets are different. And so we need to, theory need to clarify these things. For example, the condition for the type 2 migration to start, and the condition for the planet-dominated type 2. And the most important thing is that the gas flow across a gap, and the gas flow that accreted by the planet. So let me explain this. So this is a disk accretion rate, 3 pi sigma nu, in the case of the steady accretion disk. When this flow approaches to the planet, this flow is divided into the 3 components. One component is just a pass through the planet. Another component is flow accreted by planet. And the final one is stay in the disk and push the planet. Then the type 2 migration rate is determined by the planet mass divided by this flow. In the extreme case, for example, if all the gas just pass through, then the planet doesn't move. But in our case, we assume this component is 0, and most of the disk flow just push the planet. Then the planet migration is efficient. On the other hand, Modassini et al. Assume that this amount of flow is accreted by the planet. So type 2 is not so efficient. already many papers address these issues, but we need to improve, and we need to improve some formula into the population synthesis. Okay, next I move on to type 1. Yeah, as I already know, discussed, type 2 migration is so fast. If we use the isothermal formula by the Tanaka et al. For the formation and retention of the gas giant, we need to reduce the type 1 migration rate by factor 10 or factor 100. Such a reduction is too much. Unphysically too much reduction is needed. On the other hand, non-isothermal formula, of course, direction is outward or inward, but the migration speed itself is still fast enough. So the population synthesis show that we really need a migration trap. So that the non-isothermal type 1 migration itself makes some migration trap. Already show that the outward migration or inward migration depends on the disk structure. If this part is outward and this part is inward, then this location is a migration trap. But the saturation of corrosion torque is very delicate, so it's not easy to find this location, and each time evolution is also very not so easy. Other possible migration trap is a gas density jump. For example, disk inlet, here, if there's some cavity, then this is a very big jump, so it is one of the migration trap. Also, if there is a dead zone here, then in the dead zone, surface density is high, much higher than the surface density in the active zone. So here and here, also some density jump occurs. Then it can be a migration trap. Also, the ice line may also provide some source for the density jump. As already Sean Raymond talked about that, even in a solar system, if the bodies are accumulated near the 0.7 to 1 AU, then it beautifully reproduces our solar system. So our solar system may have also had some migration trap. So let me show some example for this migration trap. So this is a paper, 2010. It's before the release of the Kepler data. We proposed the formation of the closely packed non-resonant systems. So here, it's a bit simple. So here, plant seeds are formed, set up, then it grows by the planetesimal accretion, then the start, type 1. Because we set up the disk wedge here. This guy is stopped here, and the next guy is trapped in resonance, and they line up, they're trapped in resonance one after another to make some broad distribution. In the presence of gas, eccentric damping is so strong that the orbit is stable, and each mass is like 0.1 Earth mass or 1 Earth mass. So it's too small to start runaway gas accretion. So they just stay there without any accretion of gas. But when the disk has gone, they start orbit crossing. And they collide with each other and kicked out from the resonance. And then eventually we find multiple closely packed multiple supers. Of course, orbital instability occurs or not depends on the mass of a planet and how many planets are captured. So that sometimes orbital crossing occurs and sometimes does not occur. It also makes some diversity. Okay, so but not that the dead factor, so this is dead zone or thermal structure. So this migration trap problem depends on the disk detail of the disk thermal and the dynamical structure and its evolution. So we really need a consistent calculation of disk and dust and the planets. Because dust is a source of the opacity, so we also need to solve the dust evolution and the reproduction, migration, many things. Okay, so this is the last slide. So what's next? So consistent calculation of disk is it's a challenge. Also, the bulk density of closing planets is very important because it is closely related to the transit and radial velocity survey. Population synthesis provides the orbital evolution history, so it is important to calculate the bulk density of gas giant. Also, the population synthesis provides a localized ratio, so it is important for the super Earths and Neptunes. But in this case, we also need the accretion and evaporation of helium-hydrogen atmosphere. Again, the distribution of distant Jupiters. So in this case, I showed some possible paths to make such a planet through the co-accretion model. But in that case, we also need a population synthesis of the disk instability model, gravitational instability model. Only some papers started such population synthesis. Again, and then we also need so I so far showed the result around the solar type stars, but the M stars and A stars are also needed. Then we also need to address the question, so solar systems are unique or not? The answer is depends on what is the characteristics of our solar system. If our solar system, characteristics of the solar system is a coexistence of the rocky planet and the gaseous planet and the icy planets, then this population synthesis already show that such system is not rare. But if the characteristics of the solar system is having a habitable planet, then the question becomes very difficult. First, we need to define what is habitable planet. What are the calculable or observable conditions for the habitable planet? We need to fix such condition first. Okay, I stop the talk here. Thank you very much.
So let's go on with the questions. Let's start in the middle.
Okay, hi, hello. Bruno Mering from ISAC. Nice talk. I think it's really interesting that with your planet population synthesis, you might be able to answer this very important question, whether the solar system is unique. But before you can really do that with accuracy, you need to be benchmarked properly with observations. I know that's what you're trying to see, but I tend to see an over-prediction of low-mass planets in your 2013 simulations, which are not apparent in the radial velocity distributions. Is this because the observational biases are not completely, are too optimistic in your cuts, or do you still see a problem that you generate too many low-mass planets that are not observed?
You mean the population synthesis predict many low-mass planets, but observation do not? You say so?
Yeah, so I seem to see you produce too many low-mass planets compared to the ones that are observed.
Yeah, one reason is observation bias. But recent observation show that, for example, even with the Kepler 0.1 Earth mass planet, it's very hard to detect. Also, if the one Earth mass planet is at 1 AU, it is very hard. But in the case of a closing planet, Kepler already found one Earth-sized planet, and in that range, I think the observation also show that smaller planets are more abundant. So I think that it is consistent.
Yeah, well, I have a very small follow-up question to that.
Yeah.
What is the exact, because I have the feeling that your prescription of disk evolution in terms of gas evolution, how the gas is dispersed, whether it's inside out or whether it's cut off at some time. Could you tell us exactly how is that and whether you could think this could be constrained further with observations?
Yeah. In our case, we just assume the uniformly decreased gas density, and Arrivé et al. Solved 1D evolution of disk. And of course, we haven't included, for example, dead zone or and photoevaporation. And I think that it's really needed. So we need to include such a detail, not a detail, such a more elaborated disk evolution.
Okay, next question, this side.
Becky Dawson, CFA. I had a question about the eccentric warm Jupiters that you're producing in your population synthesis model. You showed the formula with the eccentricity depending on the escape velocity and Keplerian velocity. And I see how that implies if you have a single close encounter, but I think the eccentricity can get very, very large with a bunch of close encounters or if you have orbital chaos. So what's the typical dynamical history of one of those warm Jupiters that you're producing?
I said that the eccentricity is like surface escape velocity divided by Keplerian velocity, and it's a result of the multiple scattering. Just one encounter, we cannot say so. So as a result of many encounters, eccentricity, mean eccentricity of the planet is like a surface escape velocity divided by Keplerian velocity. Because if the velocity becomes higher and the eccentricity becomes larger, then the collisional cross-section is larger than the scattering cross-section. Then it's rather damped eccentricity. So this is escape velocity. If the velocity is like this, then it tends to be damped by the collision. And if the velocity is smaller, then scattering is dominated, so the eccentricity is increased.
Okay, this Günther?
Yeah, yes. Günther Wuchtel from Corot at Tautenburg Observatory. You compared to something that you call a radial velocity planet, but and your argument is that it's because transiting planets are biased.
Yeah.
But you know that, of course, radial velocity planets also have a bias, and I think we should be very careful to exclude on that categorization. Every Corot planet is a transit planet, but it's also an RV planet because it has an RV measurement, and unlike for the radial velocity planets, you know the mass, not the minimum mass. So I think, the Kepler and Corot are a shock for planet studies, I think. And being Viennese, I know what a reaction to a shock is. But I think it's important to include all observations with their appropriate biases, and then this will be a treasure trove for theory.
Yeah, I agree. But I saw that some gas giants are piled up beyond 1 AU, and even with the radial velocity, more distant planet is more harder to detect. But even that piled up is found beyond 1 AU. So I'd like to point out, I'd like to stress that point. And you mentioned that in the case of radial velocity, mass is just m sin I. But I discussed about statistical probability distribution. In that case, if the orbits are randomly oriented, then the mean mass is increased just 30% or 40% or something like that. But the mass range of the discovered planet have many orders of magnitude. I think that as long as we do some statistical analysis, statistical distribution, then the sin I effect is not so important.
Okay, next question, Alexandro.
Yeah, Shigeru, you suggested that the mass concentration at 1 AU that is required to explain the terrestrial planets of the solar system could be due to a pileup. And I think that actually, so without any need of grand TAC from Jupiter, I think that would work indeed for the terrestrial planets, but you would not explain the orbital excitation of the asteroid belt in that case, because in absence of migration of Jupiter, the only way to excite the asteroid belt as observed is to have embedded embryos to stir up the populations. And if you sequester all the embryos at 1 AU by migration, then the asteroid belt would be very cold dynamical population. So I think for the terrestrial planets, the pileup would work, but if you broaden your constraints, you're back to something like the grand TAC scenario.
Yeah, but there's another possibility like sweeping secure resonance or other process. Yeah, could work, but of course, yeah, we need to explore in more detail. Yeah.
Okay, in the middle there.
Hello, hello, hello. Ian Crossfield, MPIA. So for a number of years now, population synthesis models seem to be predicting a desert of planets at sort of 30 Earth mass, maybe 0.5 AU. And it's sort of early days, but I think we're seeing hints that that desert is not seen by radial velocity and Kepler surveys that have been appropriately debiased. Can you comment on what might be going on there?
Yeah, yeah. Previously, we stressed the planet desert, like but yeah, as I showed, recently we included some giant impact of the migrated planets. Then it produced like a 10 Earth mass planet, crossing 10 mass planet, and 20 Earth mass planet in crossing region. So it weakened the planet desert, but still we find a planet desert. Some deep, and also Jan's group and also find some planet desert. So yeah, I agree that it is a big problem. So we may need another ingredient to reconcile with the observation.
Okay. Yeah. Yes.
Hi, Shamila. Working? Hold. Hi. Shamila Miguel from MPIA. So I have two questions, actually. One is how the initial amount of embryos and the size of the embryos affect the results. And the other one is regarding with the gap opening and condition. So I was wondering, so in one case, you do consider that there is no more accretion when the gap is opening. And the other is that the accretion continues. But maybe there is something in between, because when the gap opens, then you have less accretion, and that might solve the problem that you have non-hot Jupiters or a lot of them. So I was just wondering if that might be.
For the regarding first question, as long as we set up the initial planet mass small enough, then it doesn't affect the result, because the planetesimal growth is slower in a later stage. So initial stage is very fast. So it doesn't affect the result so much. And the second point is, yeah, that point I want to stress. We need to know in more detail how much gas is accreted by planet, how much amount of gas pass through. So yeah, I agree that it is a very important point.
And the second question?
What was it? It was the second question. Yeah.
Okay, and then, okay.
Hi, James Owen-Sita. So I'm just going to sort of emphasize the planetary evaporation point you've got up there, and this may come back to the first question, is that it's been shown by Eric Lopez in some papers, and myself as well, that it's an extremely important effect that can sculpt the low-mass planet population. So I'd sort of emphasize that you need to make sure you're comparing apples with these statistical populations, and when you're looking at the low-mass population, planetary evaporation needs to be taken into account to compare to the observations.
Yeah, okay, yeah, I agree.
Okay, so if we have no more questions, thank you very much, Shigeru.